Hello everyone, welcome to our lecture series on electrostatics. In this first lecture, I'm going to give you a brief introduction about electrostatics, then we'll discuss about Coulomb's law, and also we are going to discuss about electric field and electric displacement field in this video. So electrostatics deal with the behavior of stationary charge. When we have some electric charges, so basically in electrostatics, we consider all the charges, uh, fundamentally these source charges. When we have several source charges, Q1, Q2, Q3, Q4, if I consider these to be source charges, we consider those source charges are stationary. And in electrostatics, what we are doing is we look for, if you are bringing another test charge, what will happen to this test charge because of the influence of these charges in this space. When we are bringing another test charge, what will happen to that test charge? So that is what we are discussing in this electrostatics. When we have some electric charges q1, q2, q3, let's call them source charges, and we need to find out what force do they exert on another charge q, like here. So because of this q1, there will be certain force acting on this q. Because of this q2, another force. So we are studying what are the forces exerting on this test charge. In general, both the source charge and the test charge are in motion, but we will deal with the motion of these charges later. First, we'll discuss about the electrostatic case. Then we'll discuss about the electrodynamic case. So we consider all the source charges are stationary, even though some test charges will be moving. So like it's shown here, what is the force on Q due to these simple Q's source charges. Now, the first law that we are going to discuss is the Coulomb's law. When we have a one source charge and a one test charge, what is the force exerting on this test charge due to the source charge? So we have Q and capital Q. Now, the Coulomb law states that the force exerting on this test charge is going to be, so first it's going to be proportional to the magnitude of Q, and again it's going to be proportional to the magnitude of this capital Q, and it's going to be proportional to 1 over r square. Then the proportionality constant is going to be 1 over 4 pi epsilon naught Q, capital Q over r squared, and in the direction of r. So if I have the separation here r, then we can consider the direction this force will exert is in this direction of r. And here 4 is a constant, phi is a constant, and epsilon naught, that is the permittivity of the free space, and that value is given here. Now, in this Coulomb's law, the force points along the line from simple Q to capital Q, as shown here, and it is repulsive if Q and Q have the same sign. So if both of these charges are positive, it's going to be repulsive, and if both of these charges are negative, same going to be repulsive. But if the charge of simple Q and capital Q have the opposite signs, then these charges are going to be attracted to each other. So this is the case when we have only one source charge and a one test charge. But if we have more than one source charges, so let's say we have Q1, Q2, Q3, likewise several source charges. Then we have the superposition theorem. So if I have a one test charge here, then we can calculate the total force exerting on this capital Q. We can calculate the force resulted from each of these source charge and the test charge. So first I will consider Q1 and Q, then calculate the F1. Then I will consider Q2 and capital Q, F2, same Q3 and capital Q, F3, F4, same. Likewise, we can calculate each of these forces separatedly. Then the total force that is going to be exerted on this test charge, we can write in vector form. So it's going to be a vector F1 plus F2 plus F3 plus F4. So if there are more source charges, then we can continue this up to all the source charges that we have. The interaction between any two charges is completely unaffected by the presence of other charges. So when we consider this Q1 and capital Q, we neglected Q2, Q3, and Q4. Therefore, to determine the force on Q, capital Q, we can first compute the force F1 due to Q1 alone, ignoring the others, and F2 due to Q2 alone, and so on. And then the total force exerting on this test charge, we can take the vectorial summation of these individual forces. Now, taking that into account, try this question. Four equal charges are situated at the corners of a square with the length A. What is the net force on a test charge Q at the center? So the question states, we have a square and four equal charges are situated at the corners of the square. One charge here, another charge here, another charge here, and another charge here. And the length of each side is A. What is the net force on a test charge capital Q at the center? So if I place a capital Q charge here, what will be the force exerting on this test charge due to all these charges? Do this calculation and let me know. So using the superposition principle, we can consider each of these charges separately. Now, if I consider this charge and both of these Q and this capital Q is going to be, if I assume both of these charges are positive, then there will be force in this direction. Then with this Q, again, a force in this direction. Then what will happen? Since we have the same length and the same magnitude of these charges, these two forces are going to be cancelled out, same in this direction. So we have forces with the same magnitude but opposite in direction. This pair is going to be cancelled out. Again, this pair is going to be cancelled out. Therefore, the net force on the test charge Q at the center is going to be 0. Then calculate, suppose one of these charges are removed, what is the force on Q? Do that calculation and let me know. So removing one of these charges, let's say I remove this charge here, then what will happen? This force will cancel out. Then there will be a net force in this direction with the magnitude. Now the length here is A. Therefore, length here is A over 2. So this length, if I consider that R, so R squared is equal to A over 2 squared plus A over 2 squared. So it's going to be, R is going to be equal to A over square root of 2, and then we can calculate the magnitude of the force. So that force is going to be F is equal to 1 over 4 pi epsilon naught. So because of this charge, there will be a net force in this direction when I cancel out, when I remove this charge Q here. So Q over R squared, that is going to be 1 over 4 pi epsilon naught 2 Q over A squared. That is the magnitude of this force. What is going to be the direction of this force? It's going to be towards the removed charge. So in the same way, if I consider this removing of this charge Q, I can consider initially we have this plus Q charge. Then what I will do is I will add another charge here, minus Q. So when I add another charge minus Q initially, with all these 4 charges, it is the force exerting on this test charge is 0. But then with this minus Q charge, there will be some attracting force from this positive Q charge to the negative Q charge in the direction of this direction, and the magnitude is this. So we have several methods to solve questions like this. Then can you remember the importance of this electric field? ඔයගොල්ලන්ට මතකද electric fields වල වැදගත්කම මොකද කියලා? Now we may have several situations where we are bringing some unknown test charges into a certain geometry. But if we want to do calculations for each time, let's say I'm bringing Q1 one time, then Q2 another time. So if we have several source charges, and so this is going to be the source charges, and I'm bringing Q1 charge as a test charge at one case. Then another case, I'm bringing Q2 test charge in another case. So if we want to calculate the force exerting on this Q1 and Q2 in each of the cases, then we may have to do the calculations separately for each of the case. But we have this electric fields concept. So in electric field concept, what we are doing is we consider all the source charges, and we say in an electric field, E is the force per unit charge that would exert on a test charge. So once we know the electric field, in order to calculate the force exerting on any of these Q1 or Q2, what we need to do is just take the multiplication of Q times E. So that is the significance of this electric field. So we can calculate the electric field, the force per unit charge that would exert on a test charge. So we have Q at point A, then at point B, we have a unit charge. Then what is the force that will be exerted on this test charge? Then that is the electric field. So E is equal to 1 over 4 pi epsilon naught. So here we have one charge is Q and the other charge is a unit charge over R squared, and it's going to be a vector. Vector will be in the direction of point A to point B. Once we know the electric field, then we can calculate the force at any charge in this electric field. So that force is going to be Q times E. Okay. Here's another question given. Find the magnitude and the direction of the electric field at a distance C above the midpoint between two equal charges located at a distance D apart. So there are two charges above the midpoint between two equal charges. So I have one charge here, Q, and another charge here, Q, and the separation between these two charges, it is D. And we need to calculate the magnitude and the direction of the electric field at a distance C above the midpoint between these two charges. At this point, we need to calculate the electric field. This distance is C. So we can consider that we place a unit charge here and then calculate the vectors, calculate the electric force that will be exerting on this unit charge due to this Q and due to this Q. So try this question. You need to calculate the you need to find the magnitude and the direction of the electric field at a distance C above the midpoint between two equal charges located at a distance D apart. So this distance is going to be D over 2. Here also D over 2. Then, so here it is a positive unit charge. Again, positive Q charge, if I assume, then there will be a force in this direction. Then again, here we will have a positive test charge, positive unit charge, and positive Q. We will have another force here. So since it is the electric field due to this unit charge, I will say E1 and E2. Then what can we say about the magnitudes here? What can we say about the magnitudes of this E1 and E2? So if this is R, then we can write E2 is equal to 1 over 4 5 epsilon naught Q over R1 squared, the direction of R1. And then E1 is equal to 1 over 4 5 epsilon naught Q over 5, consider this length to be R2, and the vector in the direction of this is R2. Then we have R1 R2 here, square R2. So what can we say about this magnitude of R1 and magnitude of R2? It's going to be the same, right? Therefore, if I consider the magnitude of this E1 and E2, it's going to be the same. Then let's consider angle here is theta, then angle here it's going to be theta. So I will consider horizontal and vertical components of this E1 and E2. So along the x direction, E of x, that is the total electric field due to this E1 and E2 in the x direction. So we have in the positive x direction E1 cos theta minus E2 cos theta, and the magnitude of this E1, it's going to be the same of this magnitude of E2. So cos theta is equal to dO2 over R. So we will have E1 cos theta minus magnitude of this E1 and E2 is the same. Therefore, along the x-axis, the total electric field is going to be 0. Then we will have a component of this E1 and E2 in the y direction. Then we can calculate that one next. So along the y-axis, both of these E1 sine theta and E2 sine theta is going to be, both of these components are going to be in the positive y direction. So both of these are going up. Then we have magnitude of E2 sine theta. So if you do this calculation, you should be able to get 1/4 epsilon naught 2q z over z squared plus d over 2 squared to the power 3 over 2, and the electric field is only going to be in the direction of y. Therefore, since here we considered z length, we can say it's in the direction of z. So check whether you are getting this answer. So try this one. Check your result when z is very large than d. So when z is very large than d, what we can do is we can say comparatively to the z, d is 0. Then when z is very large than d, so we can assume d is going to be 0. Then the total electric field is going to be 1 over 4 phi epsilon naught 2q z over z squared to the power 3 over 2. So this cancels out. Then we have this z and one z will cancel out. We will have z squared and the reduction in the z. So what can you see from this result? When z is very large than d, so we have electric field is equal to 1 over 4 pi epsilon naught 2q over z squared, the direction of z. So what can you see in this result? It is like, now if I have a certain charge here with the magnitude of 2q and at a point z, if I calculate the magnitude of, if I calculate the electric field here, then due to this point charge 2q at the distance z, the electric field is going to be 1 over 4 pi epsilon naught 2q over z squared in the direction of z. So when we consider the separation between the two charges is very small and the distance from the charges to the point in the space is very large, it's going to be act like these two charges are going to be act like a one point charge with the magnitude of the summation of the two charges. Okay, is it clear? අපි දැන් මේකෙදී z very large than d කියලා ගත්තාම අපිට එන ආන්සර් එකේ පෙන්නන්නේ මේ 2q charge එක total charges වල accumulation එක වගේ එක point charge එකක් වගේ act කරනවා කියලා තමයි z is very large than d කියලා ගත්තාම. So this is a kind of a useful way when you have done any calculation, you can consider a one parameter is very large than another parameter, and if the charge distribution, when you have more than one charge, if those charges are acting like a one point charge, when the separation is very large, separation from the charges to the point in the space is very large, then we can verify our result. So when the separation from point charge to the point in the space is very large, the charges should act like a point charge in the space. So this is a useful way to verify your results. Now, any questions up to this point? ඔයගොල්ලන් ප්‍රශ්නේ මොනවාද තියෙනවද මෙතනද? Then now up to now, in most of our calculations, we consider this epsilon naught, so permittivity in free space. But when we have different material characteristics, different space characteristics, then we need to change the permittivity according to that medium. So electric field, we can write is equal to 1 over 4 phi epsilon naught q over r squared, the direction of r. And if I take this epsilon naught to this side, then we have epsilon naught e is equal to q over 4 pi r squared in the direction of r. So if when I look into this parameter, now we have epsilon naught times e. So in together, when we look into this epsilon naught times e, that will include the parameters, the characteristics of the free space here. So if I change the medium, if I change the medium into epsilon, then we can write so if I change the medium from the free space to another medium epsilon, then we have epsilon e. Okay. And this epsilon times E, or if it is in the free space, epsilon naught times E, we consider that is the electric displacement vector. Electric displacement vector. So this epsilon, it is equal to epsilon naught times epsilon r. So epsilon naught is the permittivity of the free space and epsilon r is the relative permittivity in a given space. So permittivity in a given space we can calculate using relative permittivity of the given space times permittivity of the free space. Now, is it clear what is the importance of this electric displacement field? So when we discuss about when we use this electric displacement field, it includes characteristics of the medium. For a medium, this epsilon will change, and when we consider this electric displacement field, it will adjust according to the medium. So we can consider the electric displacement field. It includes the characteristics of the considered medium. Okay. So in that case, this electric field displacement field is important when we discuss about different mediums. So according to the medium, permittivity will change and the electric displacement field will give you an idea according to the change of the medium how these field vectors, displacement vectors are going to change. So in this lecture, we went through an introduction about electrostatics, and then we discussed about Coulomb's law, electric field, and electric displacement field. Also, we went through few example questions. So we are going to continue our discussion on electrostatics in the next lectures. And thank you very much.